However, card number 6 we talked about yesterday, the limit as either delta x goes to 0 or as h goes to 0. Ah, too much light. Something was weird. There we go. But the how do you see it is having us, and we saw these last year. The nice thing is I made sure, and I almost didn't, but the last second I kind of switched. Your book was almost BC's book, but I know. I didn't want you to have CalcAB, to be honest, but I decided that I thought it might be a good thing as long as you're still using it wisely. My ones that are not maybe using it wisely, you're not getting a good understanding and it's going to shoot you in the foot later. Use CalcAB and CalcAB wisely. But then coming on back. The same author from our last year, the big yellow pre-cal book, is the same author of our calculus book this year. So this isn't necessarily that weird of a problem because you've kind of seen ones like it. They dig a little deeper, right? So how are they digging a little bit deeper? They give a graph. Could we make an equation from this graph? Yeah, maybe. What's it kind of look like? A polynomial, but more specifically, it looks a lot like a squared, like a quadratic. That's been shifted down 3-ish. But if we were to go down 3, so just do an x squared minus 3. If we were to plug in when y is 0, I'm not exactly sure that would work out perfectly well. But coming on back, it does look like a quadratic. However, we're supposed to basically, for all of these questions, just think about the graph and not think about the equation. So when in letter A it says g prime of 0 equals, it does say equals, it wants you to fill in an answer, but you're estimating to the best of your ability. However, hopefully you guys were able to estimate this one quite well, because g prime of 0 looks an awful lot like what kind of tangent line? Horizontal, which means a slope of 0. Did we all get that? Now, if the maximum, no, this is a minimum. If the minimum were a little bit over, like say the minimum was at 0.1, well then maybe it wouldn't be exactly 0. But that minimum looks at 0, which means it has a horizontal tangent line. Those are important as we go on. Which would have a slope of, well that's off, 0. If I can actually get it. Let's try that. Okay, the second one. Hey, it worked. Letter B, g prime of 3. What does the slope, don't tell me a number, tell me what it looks like as far as sign. At 3, what does the slope of the tangent line look to be?
Greater than 0.
Positive. Huh?
Greater than 0.
Greater than 0. Oh, I didn't even see the g prime. It's a rough morning. What am I looking at, guys? I love our author, but he threw in something harder than I expected him to throw in. Who is this the graph of? Gracias. Ryan caught me before I went too far. What was I treating my answer like for letter A? This to be the graph of G. So since it's the graph of G prime, then question. G prime of 0 is the function at 0 because the function is G prime. So I'm really just saying who is f of 0, hence I'm not stressing about a slope of a tangent line. I'm just looking for a y value. And what is the y value at 0? Now that's a great demonstration. I literally was just going at it blind in the sense of that was my mistake. But guess what is a very common mistake for you guys for the rest of the year in AP practice problems? When they give you a graph, not realizing what it is a graph of. Letter B. Letter B, g prime of 3. What are we doing? Going to 3 and not worrying about the slope of the tangent line, saying, who is he at 3? Well, who is he? What's his y value? 0. Now, letter C says, what can you conclude about the graph of G? Can I see G? No. I don't have G, I have G prime. I have clues about G. And that's what they're asking me to analyze. What can we conclude about the graph of G, knowing that G prime of 1 is negative 8/3? Now we have a derivative value. What does a derivative value represent? Now go to our description. Slopes of tangent lines. So if I know the slope of a tangent line at 1 of g is a negative number, what does that mean about g? The tangent line is negative. Think about a curve that's negative. Is it decreasing, increasing, or constant? Decreasing. Why? Because the slope is negative. So we can say that g is decreasing at x equals 1. And why did I say we could say that again? We can say that g is decreasing at x equals 1 because
Tangent line.
the slope of the tangent line is negative at x equals 1. If the slope of the tangent line is negative, that means the curve is going down, hence decreasing. So then you guys fill in the blank for the next one. What can you conclude about the graph of g knowing that g prime is now a positive number at x equals negative 1? G is increasing because I now have a positive. Now the numbers mean at what rate it's increasing or decreasing. And I could go that far, but since this isn't like a FRQ or something, we're just going to go ahead and just say g is increasing at x equals negative 4. And technically we could say at a rate of because instantaneous rate of change, we could also say that as well. Now letter E gets a little bit harder. Is g of 6 minus g of 4 positive or negative? How can you know? At 6 than at 4?
I mean, G of 6, yeah.
How do you know?
Because the graph of G prime.
Higher on the floor.
We have to look at what we have. And what we have is a graph of g prime. And we have to figure out between 4 and 6, what do we know about the signs of g prime? All these y values are what? Positive. Well, if all these y values are positive, then I can say that g is doing what? The 3 little dots, you guys remember what those are from last year?
Therefore.
Therefore. I guess I could use the double arrow, which means this implies, but either way. And if g is increasing, then who's higher? G of 6 or g of 4? If g is going up. At 6, there will be a higher y than at 4. So if I subtract a higher number minus a lower number, it will be positive. Bridget, go ahead, kid. No, you didn't have a question. Sorry, Charlie. I just saw him. Charlie, go ahead.
For E, is there supposed to be a prime or is that a typo or?
Say it one more time. For E?
It's just G of 6, not G prime of 6.
Oh, no. It's supposed to be G. So we looked at G prime and figured out its sign, which allowed us to know how G, if all the tangent lines are positive, then the curve for G is pushing up. If G is pushing up, then G of 6 must be higher than G of 4. Does that make sense? But it would have been different, possibly. Well, actually, it wouldn't have been in this case. If it was G prime of 6 minus G prime of 4, that would have also been positive, a higher minus a lower. But no, they were asking that very, very specifically. Then letter F, is it possible to know exactly what G of 2 equals from the graph? Oh, yeah, go to 2 and then, oh, but wait, who's this the graph of? G prime. I can know whether G is increasing or decreasing at 2, but couldn't you have a point here and the curve be going up at 2? Or a point here and the curve be going up? Or a point here and the curve be going down? Do I know where or what G of 2 is? No. And for right now, we'll just say not enough info. We will definitely dig into that question a lot more. Because there are some ways to know about actual G values from derivative graphs, but we need integrals and areas and all sorts of stuff. And technically from what's given, even in this graph, we don't have enough. All right, it got hard kind of from the very beginning. But how do you see it? Could you be given a graph of a derivative and have to think through things? Yes, just to be aware. And to think through things about G, we have to think about, hey, they're tangent lines. If there are tangent lines that are positive, or I should say slopes of tangent lines that are positive, my original, which we would call our G, must be increasing or decreasing. We can tell things about the original, but we can't go finding points outright without more information. Let's go ahead and go back to our notes. Yesterday we were practicing on how to find derivatives using the definition, hence using the limit formula, or we could say the limit process. We didn't get to finish number 2 entirely, did we? We were close. If you guys can just zoom in on number 2, we have a function. We're trying to find f prime, trying to find his derivative. We do the limit as h approaches 0, f of x plus h minus f of x all over h. Why am I multiplying by a conjugate? 0 over 0, keep going, I need to cancel stuff. I need to change stuff up. So then down here, what is my next step? I did multiply by the conjugate. I did some foiling. I'm going to zoom in. What is my next step for progressing? Yeah, simplify stuff, right? So let's simplify some stuff. Let's finish this example, then let's get back into some of the other things we need to cover this section. So to simplify stuff, we could end up getting our 3x plus 3h minus, nope, that was a plus 1, minus 3x minus 1. Okay, now what can I simplify? What can I simplify? 3x's are gone, the 1's are gone. The h's now can be reduced. But let me go ahead and show that because that's kind of a tricky step for some. So all I have left on top is a 3 times h, that's important. And on bottom I have an h times, it's been factored out. Or it's written in factors. So now as you look, I have an h up top, an h down bottom. It's not with addition or subtraction, it's with multiplication. Can I reduce? Yes. And then, we didn't stop writing the limit because we know better. How do we finish this problem? Plug it in, plug it in. Plug in what? 0 for h, not for x. 0 only for h. Is Maya the only one coming? And we end up with, the 3 is by himself, his h went away. On bottom the h is gone. We have in our parentheses, square root of 3x plus 0 is 3x plus 1 plus square root of, struggle, it's coming back, 3x plus 1. So our final answer will be, can we simplify that anymore?
Yeah.
They're kind of like terms, right? There's 2 of them. So we could just say 3 over 2 of those square roots of 3x plus 1 equals our f prime of x. And for some of you who were like, you said the shortcut rules kind of work, but that this was the harder one, another way of writing this would be 3 halves times 3x plus 1 to the negative 1/2. What do you guys notice about the original and the final? How could we rewrite the original in terms of fractional power? To the positive 1/2, right? Huh. It's like the 1/2 came down and you took away 1. What rule is that, where the power comes down and you take away 1? Power rule. So there was a shortcut, but what's different, what's additional, what's there that I wouldn't expect from power rule? Where's the 3? Right? The 1/2 would come down, that's this over 2. The 3x plus 1 stays the same. I take away 1 from the power, which would be negative 1/2, which ends up putting the root in the denominator. This bottom part makes sense. That 3, where did he come from? If some of you guys remember your summer packet, there was this one about the chain rule and the inner and the outer. You take the derivative of the outer, bring down the 1/2, subtract 1, then take the derivative of the inner times 3. Oh, and that would have cut out all of this work? That's why starting tomorrow we're going to get really good at those shortcut rules, because we don't want to have to do this every time. AP says we have to understand this. But when it gets down to it, we get to solve using those shortcut rules as long as we can understand them. That was what we did today in the beginning of class. Let's keep going. All right. We have to get into some nitty-gritty stuff before we can finish this section. So, problem-solving strategies. And technically we could say, I'm going to add this in, derivative problem-solving strategies, just basic derivatives. And this isn't necessarily referring to the basic rules. Remember, that's not until section 2.2. It's coming. We can have fun tomorrow, like get our whiteboards out and like compete and all sorts of stuff. But we have to get through the ideas first. Problem-solving strategies. In homework, I do believe I purposely gave you, I think it's more towards the end of homework. Double check you have the right homework assignment from online, because I did start writing it, then I got distracted for a little bit yesterday afternoon, then I finished writing it. It ends in the 60s or something, I think. 70s? Oh yeah, you're right, the 75 through 78 it ends. But I did give you some that said, using the limit process or using the definition, find the derivative at a particular point. I'm going to put little parentheses right here, just to make it a little bit more understandable. Because so far on the page before, those little equations that we found were technically an equation for all the different slopes. Plug in x is 1 and you have a slope of a tangent line at 1. Plug in x is 2. You have the slope of the tangent line at 2. But what if you just needed to find one slope of one tangent line? There are two alternate forms of a definition derivative. One of them is the limit as x approaches c of f of x minus f of c all over x minus c. What do you guys notice about if we were to plug in x as c right now? 0 over 0, keep going. That's a hint. That's a hint. If we see subtractions of like different functions and things are a little bit weird, or of a function and a number, and if we're getting 0 over 0, maybe it's just a derivative kind of hidden in a limit form. That's one way. This would equal technically f prime of c, or f prime of x with x equaling a certain number being plugged in. It will be a number itself, not an equation. Another way of writing it would be the limit as h approaches 0, technically once again letting h equal delta x, of f of, they almost always write it c plus h, minus f of c all over h. It technically means the exact same thing. It's just being written in a different form. It's just like f of x plus h minus f of x all over h, but instead of an x, there's a c being plugged in, which is exactly what f prime of c means. And then to find the equation of the tangent line, or I should say find the tangent line or the equation of the tangent line. They can put it either way. They can just say find the tangent line. What they mean is find the equation of the tangent line. Kiddos, how do we ever find any equation of any line? We need slope. And what else do we need? A point. And point slope. Remember last year I made a big, huge deal about point slope. Y minus y1 equals m times x minus x1. We start there. It's just a plain old equation of a line. However, we say the following. x1, y1. x1, y1 is going to be our c, f of c. And what I mean by that is our point of tangency. Our point of tangency. Our x1, y1. If they just give us a c, it can be our point of tangency. What else is important in that formula?
Slope.
M. And slope of a tangent line is going to equal what? F prime of C. Now question. From up above. Is F prime of C the same exact thing as F prime of X? No. F prime of C, a number is getting plugged in. And when a number gets plugged into an equation, what do we get out? An equation with variables or a number? Uh-huh. So this should be, when you solve for it, this should be a constant. One of the biggest mistakes for tangent lines is A, not knowing where to start, and B, plugging in the derivative, f prime of x, instead of plugging in the one derivative, the one slope at the one point. At one point, there can only be one slope. This is forever number 7. However, listen, there are some cards like the definition of continuous and intermediate value theorem. There are some cards where you just have to memorize the whole thing. And there are others that are more fill in the blank. Guess what this one is? It's more fill in the blank. I'm not going to have you state the entire card, but I might ask for an alternate form of the definition of derivative. Or the limit formula for finding the derivative at a point x equals c, and you have to give me one of these. Or I could say, what's the process for finding the equation of the tangent line? I'll ask them separately, just so that you guys have a heads up as to how to study Forever 7. But that is Forever number 7. A couple more seconds for you guys to label. Let's keep going. Okay, so what if they said find the derivative? What's another way of saying derivative? Slope of the tangent line, true. Or couldn't we just say f prime of x? Is that okay?
Yes.
Find the derivative and the slope of the tangent line followed by the equation of the line. So find the derivative and the slope of the tangent line. Which tangent line? Read the problem, kiddos. How many tangent lines am I finding? One specific. Okay? At x equals c. In this case, at x equals 2. Followed by the equation of the line. Find the derivative and the slope of the tangent line followed by the equation of the line. Now, we're going to do this a couple different ways. First of all, we are getting ready for our shortcut rules. So let's just double check. This is hopefully an easy-ish one. What would f prime of x equal? Bring down the 2. X, take away 1 from the power, plus bring down a 0, right? The derivative of any constant is 0. So that's the derivative, all right? We'll just go ahead and leave that. That's the derivative. But I want to go ahead and practice that formula on the page before. Let's find f prime now of, who's my specific x value? 2. Now, since we're practicing in this section a limit formula, let's go ahead and practice one of the different versions of the definition, okay? Let's go ahead and use, doesn't really matter too much. Let's go ahead and use the first one. So the limit as x approaches c, which is 2, of f of x minus f of c, which is 2, all over x minus 2. Let's see if we can plug into this one okay. All right. Who's f of x? Oh, wait. Rewrite your limit. Just like we did with the other definition, we got to put in our pieces. Who's f of x? Yeah, take the whole equation. X squared plus 1. Minus, who's f of 2? Plug in 2. So 2 squared is 4, plus 1 will be 5. We'll get there in a second. All over x minus 2. Guess what happens if I plug in x is 2? 0 over 0, keep going. Hence why we're keeping going. We're plugging in stuff. And then when we go to simplify, we end up with the limit as x approaches 2 of x squared plus 1 minus 5 all over x minus 2. Nothing is canceled out yet, but can I keep going? What's 1 minus 5? Minus 4. Hey, why do we like that? we can factor it. So we can say the limit as x approaches 2, x plus 2, x minus 2. I'm removing the x minus 2. I kept writing my limit because I'm smart like that, so that I can remember now at this point, how do I finish this problem? Plug it in, and my final answer is 4. Now hold on. Once we do the shortcuts, what's another way of finding this? What's another way of finding this? F prime of 2 just says, plug it in. Oh, hey, 2 times 2 is 4. Yeah, we're getting there. But just so that you guys know, this does just mean the derivative of f at x equals 2, which is 4. Now how do I finish off and do the equation of the tangent line? Y minus y1, or in this case, technically, y minus f of 2 equals f prime of 2 times x minus 2. Who is my y1? They didn't give it to me explicitly, but who's the y at x equals 2? We found it. It was down here. Plug it in. 5. But we had to find it ourselves. Who is f prime of 2? 4. And who's x minus 2? Well, he is himself. Now some of you are like, you were lazy. You should have kept going to get it in slope-intercept form. But if it's not a multiple choice problem with multiple choice answers that we have to, you're going to get really used to this, make it match. We can stick it to the man and be like, we're right, if you don't tell us to simplify more, we won't. And some of you are going to love that stick it to the man phrase. Okay, one more big idea. Differentiability. It's technically the last thing you guys see in homework. I don't think you see it any earlier. You see it in problem 75 to 78, and you're allowed to look at graphs for those. There are other questions, but I don't want you guys to stress about finding derivatives the long way when we're about to really work on finding derivatives a shorter way. So I'm letting you guys just do the section with differentiability of graphs, and then we'll come back to differentiability once we're taking derivatives a lot quicker, okay? So, this is like the notation page. This is the figuring everything out page as to what these terms mean, but hopefully we've kind of been getting used to them. For instance, derivative terms. Hold on, we have one more page, right? Then we're done. Those are all homework helps. Okay. Derivative terms. We have derive or differentiate. What do they mean? To take the derivative. To derive, just think, calculus is driving me crazy, right? So if you're driving on the road. Derive is a verb. What's it mean? To find the derivative. Differentiate is a verb. It means to take the derivative, okay? So to derive, to differentiate, they both mean the exact same thing in the sense of you're taking a derivative. Notation. To take the derivative of, to derive a function, the main notation is d dx of, we know that grouping symbols can mean of, like function notation. So take the derivative of, for instance, f of x, we would say take d dx of f of x. There is another way of doing it technically where you could do a capital D with a little x of. They basically mean the exact same thing. These are ways of saying, like, hey, it's time to take the derivative. It has not been taken yet. It has not been taken yet. Differentiation. Is that a verb? No, it's a noun. Differentiation, I think it's even technically the title of chapter 2. But differentiation is basically the act of finding derivatives. Finding derivatives, solving for derivatives, working with derivatives, etc., etc., etc. It's just the noun, differentiation. So when you're practicing differentiation, you're practicing how to take derivatives. Differentiable, what's that? someone's likable, it's kind of like an adjective, right? Differentiable, it's like an adjective. It is a function with derivatives, let's just say with existing derivatives. And differentiable, as we'll see, existing, I can't spell. Or we could say a function able to be derived, but some functions can be derived at many places but not at another place, kind of like how many functions are continuous but have a discontinuity. Many functions are differentiable almost everywhere but have a few places where they're not. And one more thing to do with notation. We've already talked about a derivative can be seen as f prime of x. Technically, we've also already seen that a derivative can kind of be found by looking within a limit. However, there are a couple other ones, the most notable of which would be dy dx. These are all nouns. These all represent a first derivative. And you're like, ooh, maybe there are more than first derivatives, and that is true. However, that is not for today. So f prime of x, that's talking about a derivative. The limit formula, that's talking about a derivative. dy dx is talking about a derivative. You can think dy over dx. We'll talk more about this notation. It's actually called differentials. There's one more page. I told you there's one more. Come on, come on. This is for the very last section of homework. Yeah. Yeah. I'll have to be buttoned loose. You see that? Okay. Last one. Connection between differentiation and continuity. And I'm going to say actually let's change this. Differentiability. Differentiability and continuity. I know now it's awkwardly off. There we go. Connection between differentiability and continuity. Long story short, if a function is not continuous, it's not differentiable. If it's not continuous at a point, it cannot have a derivative at that point. If a function is continuous, it may be differentiable. There are two exceptions, two main exceptions. And the two main exceptions are a function is not differentiable at sharp points, give me a second, aka like the vertex of an absolute value. At sharp points, the derivative does not exist, and at vertical tangent lines, the derivative does not exist. And we'll talk more about that why as we continue learning about derivatives. This is one quick little thing to have. You're going to need it for the last 4 problems of homework, and you're just looking at graphs. Do they have vertical tangents? Do they have sharp points? If so, no derivative exists there. Bye, guys.
So it's not